Hello, everyone. Can you hear me?
Yeah.
Okay, great. So welcome to the HBS Lab group meeting, the annual group meeting. Okay, so today is May 2022. We'll begin our short presentation from members of the HBS Lab today, talking about the accomplishment and the work research in the last 1 year. Okay, and less during the activity during this time. One important thing I want to mention is that this kind of activities is important because in a conference this is how you present your research. Okay, disseminate the research output to the general public and explaining about what you've been doing. Okay, and practicing like this one will help in your career. So we'll have a presentation today from PhDs, masters, and undergraduates, and we have high school students too here, right? So we'll begin from PhDs, and who's the first presenter, Pandip?
It's me only. The
Okay,
first presenter is me.
so please share your screen and let's go.
Just give me a second. Sharing my screen. Okay. So are you guys able to see my screen?
Yep.
Okay. So let me just share the full screen mode. Okay. Now are you
Yep.
able to see the full screen mode?
Yep.
Okay. So let me start. So hi friends. Myself PS Matharu. I'm a PhD candidate from the mechanical department of the University of Texas at Dallas. So as you can see, I'm working in the HBS lab, and the major research areas for me are underwater soft robotics, artificial muscles, soft robotic skin, and also on the humanoid robots. So why do we do research on biomimetic soft robots? The major fundamental areas of working are uh, basically these robots are soft. They use both the conventional and the non-conventional actuation. They they can be used for sensing and control in various different applications. Plus the powering aspect of these robots. So these are the fundamental areas of working of soft robotics. Now, what are the major objectives to make a robotic design? Why are we making a soft robot? So basically, we are making a soft robot to understand the behavior of non-conventional uh, actuators under various conditions in water. We are designing and manufacturing self-contained underwater soft robots. We are testing these soft robots to perform different tasks such as surveillance and transportation. And we are also trying to understand the different non-conventional muscles, the actuators, by doing modeling and the experimental tests. Uh, the major areas of work that I have been doing over the past year uh, are shown in this slide. So in the underwater soft robotics domain, the first robot that I'm working on was the 3D printed uh, Jellyfish Robot. This was a project that was sponsored by the ONR. So basically, the ultimate goal of this was to make controllable geometry of an underwater soft robot, basically to make it uh, manufacturable and to utilize swarm of these robots. Number two was the battery powered jellyfish. There is a problem in the underwater soft robots that most of the robots are using wires to get their power, or different methods, but none can say that they can be powered on their own wirelessly. This is the purpose of using the battery powered Jellyfish, where I'm trying to use the wireless communication system plus the artificial muscles to actuate the robot with the battery inside the robot. Number three is the hydrogen powered Jellyfish, which is a pneumatically actuated Jellyfish for the cost to make it cheaper basically. And finally the Jelly Z. This is a TCP actuated robot, which is quite cheap. Its cost is under $15. It's a it's a soft robot, and it has no motors and pumps. Uh, now, why do we use the artificial muscles? The artificial muscles are used uh, in response of the change of the environment. They are used to control. We can control the level of stroke of these muscles by changing the length of the fiber, by treatment in the atmosphere where we provide heat, and we also change the frequency of the actuation. We can also control the number of plies to actually increase the amount of load that these muscles can take. Moving on, we are we are working on some fishing line muscles. These are both self-coiled and mandrel coiled. Right now, currently we are working on mandrel coil muscles, of which we are using in the soft robotic skin, and we are seeing the performance of these muscles are comparable with the shape memory alloy coils. These are compact, lightweight, flexible, and strong. Here in this slide, I'm showing the fabrication process of these muscles. Step one is retwisting. Number two is putting nichrome. Number three is coiling. On the right hand side, you can see different photographs of these muscles when loaded and not loaded. Now, the focus of the fundamental scientific contribution is by understanding the fundamental physics of smart materials, understanding the constitutive relationships, and also by understanding to how to incorporate these constitutive relationships into the robotics model. So my major area of work in my PhD is to investigate all these aspects and to make a totally sensing and totally controllable underwater soft robots with the soft artificial muscles. What is my ultimate goal? As you can see in the screen, my ultimate goal is to make an autonomous smart robot that can go underwater, which is soft and which can explore uh, up to various depths inside oceans and seas. As we all know, oceans and seas are not being explored totally. So these soft robots will help in future to go deeper down the oceans and explore various things in oceans. So far, this is my second year of my PhD. These are the papers which have been accepted, submitted, and currently I'm making. So that's all from my side. Thank you. And I would like to thank Dr. Ray Bowman, Dr. Jack Costello, Dr. Jonas, who is my guide, PhD supervisor, and Dr. Sean Collins. Thank you.
Great, good job. So let's give hands for Pondip.
Thank you.
Great questions. So for Pondip from anyone. It's a lot of work, Pondip. I think the publication is also coming along and everything is going good.
Yes, Professor.
So just I will start one or two questions for you. So
Sure.
what advice do you give for now for a PhD student who's starting? Uh,
Uh,
uh, so, you've been doing a lot of experiment actually and things like that. So what do you suggest?
for someone new, firstly, even I am currently in my PhD, so yes, I can speak from my experience. I think if someone wants to start his or her PhD, uh, the first thing is to know about your area first, as you always say, read papers in your area so that you have a command of that area, the base set, so that from that base you can always do some new things, some novel things in your work, which will make the quality of your work better, because you are always knowing the current research going on. So that is my advice. And yes, to always be patient and stay smiling. Like
Yep. Yes, so Joe, I think thanks, Poundy, for bringing up that. Okay, so because so just PhD is a lot of things. Sometimes you may get excitement, sometimes you may not get results. So frustrating. So patience is very important. Yeah, it's a journey, long, deeper and wider aspect that you need to cover. So
yes.
that's good comment.
And
Any question for Pondip from anyone? So we are all learning also. You see, whether you are a professor for so many years or short, it's just always learning. That's why you just keep reading papers and do research and find out what's going on. So we are always learning. Okay.
yeah.
All right. So let's move to the next. If
uh,
there is no any question for Pondip.
okay. So uh, we
Who's the
can,
next one?
yeah. I think
Jani?
next is
I
Gianni.
think I'm the
Yeah,
next one. Yeah.
yeah.
Okay,
Gianni
I can.
goes.
Okay, sounds good. Okay. Okay. Hi everyone, I'm Gianni Stano. I'm a visiting PhD student here at UT Dallas. I've been working in the HBS lab, since September under, the supervision of Dr. Tadissi. I come from Italy, Polytechnic of Bari, and unfortunately next week is going to be my last week here working for the HBS lab. And we can summarize my research using this title, Additive Manufacturing for Soft Robotic. Basically, a soft robotic is based on a lot of different pillars. One of those pillars soft robotic is based on is the fabrication of smart structures. For smart structures, what is a smart structure? A smart structure is a structure, with embedded sensor able to provide feedback. So generally, using a traditional manufacturing approach, fabricate something like that requires a lot of manufacturing steps and a lot of assembly tasks. We try to overcome this problem using the 3D printing technology, in particular fusion filament fabrication technology, FFF, also known as fusion deposition modeling technique. Basically, we use a dual extruder 3D printer to fabricate in the same printing cycle both the sensing elements, you can see in the first figure over here, the sensing elements, so the strain gauge, the capacitive force sensors, and also the passive structure. So we, in this way, we didn't have any, assembly task, and only one manufacturing, step was involved. Also, we abruptly, increased the automation degree of this, manufacturing method, because we also embedded a shape memory alloy inside the robotic finger. We embedded the shape memory alloy using, exploiting a pick and place robot. We basically stopped the fabrication. We used the pick and place robot. We embedded the shape memory alloy. Shape memory alloy is an actuator, and we resumed the fabrication. And it was very important, the study of the materials that we used, that we extruded using the FDM technology, because we use a PCL material. PCL is well known for having a very low, extruding, very low, melting temperature. So it means that its temperature doesn't, affect the shape memory alloy programming. Also, I mean, we did a lot of tests on this finger, and here you guys can see one of the tests that we performed. In particular, we, got a change in resistance thanks to the embedded strain gauge that was completely 3D printed as a function of the actuation. So it's a very good result, considering that we have we had a very consistent change in resistance after every cycle. Another pillar, of soft robotic is the bio inspiration. Basically, we can, I mean, just take a look of our body. We have, you know, stiff materials like bones connected each other by means of soft matter, like, for example, cartilage or whatever. So basically, we use the same technology, the same manufacturing technology, the FDM technology, to create this kind of bio-inspired, you know, structure by extruding at the same time a very stiff material and an extremely soft materials. This is a very new topic and a very challenging topic that can potentially, I mean, push the role of the additive manufacturing a lot for the soft robotic in the soft robotic field. So we basically studied, you know, how process parameters, post-processing, and some design interface, you know, can give us some, you know, benefit for the stiff soft material addition, and we came up with you know the optimal configuration, and also we fabricated a couple of bio-inspired structure. Now I'm playing the video. It's gonna start soon, I hope. Yes, this is one of the bio-inspired structure we fabricate. Is a finger, and the gray part is a very stiff material, while the black joint is made up of a very extremely soft materials, and there is the shape memory alloy inside. And now, guys, you can see again when we activate the shape memory alloy that we have a very fast response of the finger. And also, if you guys you know, try to bend your finger right now, you are gonna see that you are gonna have almost the same, you know, bending that we got using the 3D printed finger. And also we also 3D printed another you know, structure that we call the 3D printed bender. Is literally you know, a structure with a soft joint and eight shape memory alloy, you know, surrounded the structure. And as a function of the shape memory alloy that we activated, we got different you know, bending motions. So that's it. I'm done with the presentation, and I will just like, you know, finish. I would like to finish just saying that additive manufacturing, in my personal opinion, is fits very well with soft robotic, you know, requirements. And I really do think that in future additive manufacturing will be, you know, extensively used for the fabrication of soft robotic, and also additive manufacturing might help a lot soft robotic to grow over the next few years. So that's it. I'm done.
Great. Thanks, Gianni. Excellent.
Thank you, Professor.
Yep. Let's give hands, virtual hands, everyone, to Gianni too. Questions from you guys. I don't want to be asking or the only one asking questions. From a question from anyone.
So Gianni, I have a question. So
Yes, go on.
what's your future research area? Like you are going, like once you have the experience now of doing work in the HBS lab. So what's your future research goal?
Mm. I mean, it's a good question. I'm gonna, you know, finish my PhD in November, so I think I will mostly focus on writing my PhD thesis right now. So when I'm gonna get back in Italy, I focus on that one. But I would like, you know, to keep working on this kind of, you know, stuff, additive manufacturing of sensors, you know, embedding actuator and actuation systems inside the soft structures. So yeah.
Nice, man.
Thank you
Great.
for
All the best to you.
Thank you, Wandi. Thank you.
Great. So I do have one. So Gianni, the slides, while the slides are here. So I think the problem is very this problem of manufacturing sensor actuators, the passive structure, wiring, everything is very complex, right? So to make smart structure, so even including in the future controller, circuit diagrams and everything is a big area of challenge for everyone, and there is no perfect solution so far, right? So I think the capacitive sensor, the one on the left that you have, capacitive sensor, you have also the strain gauge for flex sensor, the touch, and the entire passive structure. So now my question is, how small, using the additive manufacturing with the FFF, right? How small can we make this this kind of printing
This is a good
potential?
question. Yeah, this is a good question. I think, if you want to have, good, feedback from the sensors, for example, a strain gauge is not supposed to be less than, but just because it's fabricated with additive manufacturing, it's not supposed to be, is length less than maybe 3 centimeters.
Hmm. Hmm.
Yeah,
Great.
the scalability, it's a little bit a problem for FDM, for FFF fabrication, especially
Mm.
when you want to fabricate very small structures.
Yeah, but I think for humanoid robot, for example, finger or prosthetic, I think this is a good approach because we have been 3D printing, using 3D printing for the last 10 years and make
Mm.
robots, but we have several integration, which is now you are solving that problem. So I think this is significant.
Okay, yeah.
Yeah.
Thank you. Yes.
All right. Okay. Thanks, Gianni, again, once again. Let's move to the next.
Thank you, everyone.
Thanks, Gianni.
So, Professor, next speaker is Ovi. So you can share his
Okay.
video if you can.
Okay. So I'm gonna share OV. All right, everyone. I'm sharing Ovi's presentation. So Ovi is not here today. So I'm gonna show his slide pre-recorded. Okay. Here we go.
Hi everyone, I am Ovi. I am working on additive manufacturing of soft materials using custom-made 3D printer. Uh, we all know that the fabrication of extremely soft structure capable of performing bio-inspired complex motion is a challenging task in soft robotics because of the issue in silicon molding, which do not allow us to print complex structure, and then the alternative innovative fabrication technology are very expensive. So to solve this issue, the current research describe a custom-made inexpensive 3D printing setup capable of extruding silicon, which is shown in this figure. At first, to understand this custom-made printer's capability, two process parameters are studied, and they are printing speed and build plate temperature. After studying these, circular and square object with maximum dimension of 175 millimeter has been fabricated, considering the build plate is 200 into 200 millimeter. Another important aspect in this silicon is silicon curing. To improve the curing, an additional heating element has been installed from the top to provide heat directly to the recently extruded silicon, which results structures with a maximum height of 30 millimeter, which is shown here. Finally, the proposed custom-made 3D printer was used to manufacture multiple types of silicon skin with embedded shape memory alloy actuator. This work has been done in a single manufacturing step with autonomously without any kind of human direct intervention using a pick and place robot that used to embed the SMA. Two types of silicon skin has been manufactured, and one is this traditional silicon skin and which doesn't actually have any pattern, and three type of silicon skin have been printed, and there one is SMA in the middle, one is SMA in the diagonal, another one is SMA in dually. This silicon skin after embedded is done, it is characterized using power supply, and in the time they are tested at different current inputs, and this skin demonstrate complex motion that recall the behavior of several animals, including an elephant trunk, a cuttlefish, and a caterpillar. So these are the MATLAB plots of this skin movement. And now I am going to talk about another type of silicon skin which has been manufactured and patterned, uh, manufactured. And this is patterned silicon skin. Three type of patterned silicon skin have been printed here. One is chase, another is three line, another is crown. Different structure shows different kind of motion as shown in the figure. And these are the MATLAB plots of the silicon skin movement, which has been done using the tracker software. The patterned structure demonstrated unique behavior, and the most important significant thing is here, they show out of plane deformation. The achieved result demonstrate how soft robotics can be benefited from the silicon based material extrusion, which is combined with a pick and place robot. And numerous interesting application can be possible with the proposed 3D printed artificial skin, including soft gripper, walking robots, and a soft robot carrying object and jumping robots. This video shows the manufacturing process of the silicone skin printing. Here we show the out of plane deformation of the some of the silicone skin. Now I am going to talk about 3D printed soft robotic finger for soft robotic gripper. This is the CAT file for the soft robotic finger, which include the holder for gripper assembly, slot for SMA spring as actuator, and also slot for spring steel to give the finger enough solidity so that after actuation it comes back to its initial shape. And here is a picture of actual 3D printed soft robotic finger with embedded actuator and spring steel. After printing several fingers, this is characterized using the power supply with different current outputs. Current has been used in this research 3.4 ampere to 4 ampere. Current applied for 3 seconds, and then there is a 15-second gap for finger to go back to initial shape. And uh, the study has been done for 5 seconds, which you can see in the video. And it has been found that when the current is higher, the bending angle is more. When it is 4 ampere, it reaches to 60 degree, and when it is 3.4 ampere, it reaches to 50-degree bending angle. Hysteresis effect is also visible in these fingers. This video showing the characterization process. Now the next research is going to be focused on how to increase the bending angle so that the stiffness is more. Also, the finger will be more applicable efficiently in the soft robotic gripper. Using the research done by the Mutlu et al. In this figure, two new types of finger has been printed. One is human type, human-like, and another is finger without joint, just like what we did previously. After printing, the characterization is done using 3.7 ampere current by applying for 3 seconds for one cycle. It has been found that the bending angle is far superior for on human-like finger. For human-like finger, the bending angle is 92, and which is 35-degree more than the finger without joint, which is very, very significant. Due to the human-like joint in the finger, we achieved these results. Although to 3D print this kind of finger is very complex and almost impossible to mold. By printing finger with joint, we can achieve more bending angle, more stiffness, which is more suitable for soft robotic gripper to hold heavy, bigger, and complicated object. Uh, Thank you everyone. Gianni assisted me in these projects, and I have also worked with Gianni for FDM printing projects, and Gianni will present about those interesting work. Thank you.
Great. So we don't have question for Ovi, but I think the work is very interesting. It's a lot of work. Let's give hands, everyone. So for Gianni, for Ovi. Okay. Any question? Maybe Gianni can answer some of the question, right? So you guys are working together. So what's the frequencies? So the frequency, the last one, the finger, the bending, this one, the one this shown slide. What's the frequency?
I think it was 3.7 ampere for 2 seconds and 10 seconds of cooling down.
Okay, 12. So 1 by 12. Almost. So it's good relatively for SMA. I think the spring still helped it to return back, you know, so that's the effect, right?
Yes, the spring steel helps a lot.
How many spring steels are here?
One.
Okay. What's the thickness?
I don't remember.
Okay, maybe. Okay.
The thickness is 0.2 mm.
Okay, 200 micron. Okay, so I think that's good. All right. So let's move to the next. Thank you for the question, and thanks Ovi for the presentation and sending slide. Okay. Pandip, who's the next? Abhishek. Okay, again, Abhishek I need to turn on the video then.
Yeah, so, Abhishek and then Drew.
Okay. The Drew didn't send, so I think let me display Abhishek's video. Okay, he sent pre-recorded.
Sure.
Hello everyone. My name is Abhishek Singh. I am a PhD student in mechanical engineering working at HBS Lab under Dr. Jonas Tedesi. My main
Can
research
you
is in
hear?
the area of socially assistive humanoid robots.
Yes.
Mhm.
My area of research is in developing socially assistive humanoid robot is targeted towards assisting elderly population and patients suffering from Alzheimer disease. As it can be seen, according to CDC data, number of people suffering from Alzheimer disease will nearly triple by 2060. So, developing socially assistive robots for this purpose is really active, and that's where my focus is right now. Over here, you can see two of the socially assistive robots. On the left, there is the HBS humanoid robot, and on the right is the buddy robot. So these are being developed currently, and they uh, with the purpose of supporting patients in their daily activity living task. And one of the main criteria is that these robots should be affordable, lightweight, and easy to manufacture. And these robots consist of mechatronic systems that also utilize artificial muscles for finger movements, where it is difficult to put servo motors as they tend to make the robot arm more bulky and requiring more complicated mechanisms. For finger actuation, TCP actuators and SMA actuators are some of the examples of artificial muscles. Over here, you can see they don't take too much space, and the operating mechanism is also simple because they are less bulky and easy to operate. Many different kind of complex motions can be achieved from the fingers with the help of these artificial muscles. The the goal of this project is to eventually support cognitive functions and provide emotional support to the patients, as well as enhance the security and safety of the patients by detecting falls, alerting authorities and family members in case of emergencies, uh, improved interaction, friendly appearance. So all of these can be achieved with the help of Internet of Things, integrating different devices, incorporation of artificial intelligence, as well as uh, installing a mobile base so that it will provide more autonomous capabilities to the humanoid robot and increase its functionalities. That's all for my presentation. Thank you.
All right. Okay. So let's give hands for Abhishek, everyone. So for the updates about Alzheimer and the social robots um, for assistive role. So the next is Drew.
Yeah,
On you.
next is, yes,
So I
next is
don't have a
Drew.
slew from Drew. So
Okay.
maybe we should move to the next. Okay.
Next is Shubhankar. So now we have the master's
Okay.
students.
We start the masters. Okay. So
Shubhankar.
Shubhankar sent this summary. He's not here, right? Yeah. I think I
No.
have his slide. So where is Shubhankar? It's Shub. Fludo Jelly. Here it is. Okay.
Hello, I'm Shubhankar Kave. I'm a master's student at the Engineering Department at UDD. I'm currently working under Dr. Jonas Tedesi on the Fluorogeli project. So, to start with, what is Fluorogeli? So, as the name suggests, it's a biomimicry of a jellyfish. So, similar to the working of a jellyfish, which works by jetting out water by movement of its legs to achieve motion, the Fluorogeli works similar to that. The Florogeli uses the same principle by jetting out water using the movement of its legs of the Florogeli robot to create motion. The Florogeli is a soft actuator actuated robot which is pneumatically actuated and controlled using solenoid valves and remote controlled circuits. So coming to the circuit of the Florogeli. The circuit of the Florogeli consists of a transistor as a switch, a 3.3 voltage regulator, a diode, and the XBE wireless radio transmitter and receiver. So as you see, the circuit is not much complex and is kept simple for now. The Fluorojelly is an autonomous underwater robot which can be controlled remotely and can be used in a wide range of applications such as underwater rescue operations, underwater monitoring and surveillance, etc. Currently, the Fluorojelly has achieved underwater movement autonomously while being remotely controlled. The video shows the autonomous working of the Fluorojelly robot underwater. The video thus shows that the Fluorojelly has achieved flapping motion. The next work of the Fluorojelly is stabilizing the robot to maintain controlled directional motion. By this, I mean achieving balance between the buoyancy and the weight of the robot while maintaining the motion of the robot. Thank you.
Okay. All right. So let's give hands for Shwankar, right? So I think this
Yep.
is the pneumatic actuated jellyfish robot. The first slide, the natural jellyfish is also great, right? So
Mm-hmm.
the in the first few slides. So I like this
Hello, I'm
the
Shubhankar Kasle.
natural
I'm a master student. Hello,
movement of a jellyfish belly. I think this structure is very magnificent. Okay, so let's move to the next. Who's
Uh,
the next Pondi?
Next is Akash.
Akash the sky. Okay, Akash. Yeah, here it is. Okay, I'm gonna display Akash's.
Hi everyone, this is Akash. I've been working with HBS Lab for over a year now, and this is the summary of work that I have done in past 1 year. I majorly work in the domain of underwater robotics, and you can see multiple jobs that I have done, and I'll take you through each one of them individually. So at the bottom left, you can see a model of Jboss Camera. And now the Jboss Camera is a smart camera system that we have used for our jellyfish project. Now, what it does, it is used for the object detection purpose. How it works is explained just over the model of the camera. You can see that the working principle of a Jboss camera given against the working principle of a standard camera. That is how a Jboss camera works and is able to detect the object. Now at the top left, you can see the different objects that the camera is able to detect. And now we actually used a multiple uh, two three modules during our experimentation, and this was the module that we used for the final experimentation. You can see it is able to take up it is able to detect uh, different different objects such as animals, cars, ship, a person. So that is all for the object detection. Moving to the center of the screen, you can see the simulation you can see the muscle simulation. Now what I have done here is that we have taken a 3D model of a artificial muscle, particularly the TCP fishing line muscle, and we provided it with the equivalent thermal input that a regular muscle receives in actual operation. So, and we try to simulate the process of the I mean the working of a muscle in a simulation software, and these are the results that we have got. At the top screen shows you the change in temperature, and the bottom screen shows you the deformation of a muscle. Now you can see it mimics the original working of the muscle. So this again, this is not the 100% accurate. This is not up to the 100% accuracy. We couldn't find the exact materials, and that would be the plan for the next semester, to get this thing work. Get this thing to work 100% at 100% accuracy. Now, moving to the right, you can see the CFD simulation I have done for the jellyfish robot swimming up in the water. This is the result. Moving down, moving down, you can see the electrolysis screen. Now, during the development of jellyfish, we had like a lot of problems. This was the major problem that I and Pavandeep faced. The jellyfish creates since because of the contact of the artificial muscle and the water, it creates the electrolysis, and the electrolysis has a major effect on the swimming of jellyfish. Now this is one of the biggest problem that I want to solve in upcoming semester. On the right you can see the two different projects that I worked with, different teams. A Peltier project I've worked with Ripudaman and Sanjana, and at the bottom you can see a starfish robot that I have tried to work with Gianni and Ovi. The next screen shows you the my plan for the next semester. These are the three projects I would like to pursue along with the projects that I'm working with. Now on the left you can see the soft creeper, and in the center you can see the busy fish. These both of these are actually developed during the coursework of in the previous semester. These I'd like to pursue these projects with the Abhishek and Ripudaman. And on the right you can see the starfish again, the same project that I showed in the previous screen. I'd like to complete a working model out of this, which I couldn't do it in the last semester. So this is the overall summary of my work and the plan for the next semester. Thank you, guys.
Great. I think so. Let's give hands for Akash. I think they are very interesting, and this is going to be a great master's thesis too. It's great. I didn't notice some of the so some of the videos I didn't notice.
Hi everyone,
So
this
let
is
me pause.
Akash. I've been
Yeah, but the simulation is also great. I think that will strengthen the theoretical part, flow simulation as well as the computation of the muscle. And I didn't see about the starfish actually. I didn't notice so far, but that's great. Any comments, question? And I think Akash is collaborative too, so you work in multiple projects, right? Any comments? Okay, so let's move to the next. Who's
Okay.
next?
So next is Sanjana. I
Sanjana, she's
don't
not here.
think
So, we should congratulate. Let's
Ripudaman. Okay.
even though they are not here, Eric and Sanjana, they graduated. They successfully defended their master's thesis. So let's give them a hand for Sanjana and Eric. All right, well done. So they did very well. Thank you, guys.
Ripudaman is next.
Okay, Ripudaman is not presenting, so the next.
Okay. Next is Arun Chalam.
Arun Chalan. Okay, Arun sent me a video, so let me display that. AR, right?
Hello everyone. So I'll be speaking about my research summary today. So the short period of time in which I've worked with the Hbs lab. So my work is focused completely on the Kraken robot. So for the first step of my work, it began with the inspection of the robot in its current form. The robot is completely deassembled or disassembled right now, and it's been sold in its individual components. So after which I proceeded to the cataloging of the components of the robot, which are available to us right now in the lab. And so a check was completed for each of the components to see if they are in good operating condition or not. The first step of the work was to actually test each of the four elastomeric arms of the robot, for which a simple setup was made with a stand and a clamp for each arm. Since each arm is cable actuated with the stepper motor right now, so by applying the same stepper motors from the robot, a separate shaft cap was designed and 3D printed for the robot for stepper motor, using which each of the four arms are being test it to see if they're in good condition or not, and to see for defects. So after which the next step is to assemble the robot with the existing available, to check the robot for its performance in a submerged environment or sandwater environment. So once that's finished, the next step would be to try and switch the actuation mechanism of each of the arms from the cables to full SMA actuation. So the majority of the work for this robot will be done over the summer, and yes, until now, this is the extent of the work which has been completed with the robot. Thank you.
Okay, so I think Arun Chalan's work is basically on the Kraken robots, underwater octopus-like robot, right? So working with Pond Deep. Okay, let's
Yep.
give hands for Arun Chalan. So he's just started. So again, right?
Yeah.
Yep. So the next, who's next, Pond Deep?
Next is Ebenezer.
Okay, Ebenezer is new, so I think he don't have slide, right? Doesn't have slide. Is that right, Ebenezer?
Not Professor. I don't have anything to present. Just I'm new. I'll present
Okay,
next
yeah.
time.
Yeah,
Thank
you
you.
just, yeah. Okay, now
All right.
let's move to the next.
Egan.
Okay, Egan. Oh,
So,
before Egan,
yeah.
so I
Yeah.
think let me finish the one because I'm sharing my slide. So let me finish the one that I have. Jacobs
Okay.
present. Maybe
Yeah.
let me go for Jacobs, right?
Yeah. Yeah. The
I have
masters are done
Jacobs.
also.
Okay, I have Jacobs and I have Jonathan's. Let me put those two. Okay.
Yeah. All right. All right.
All right. So I'll start from Jacob.
Hey guys, my name is Jacob Edwards, and this is my research recap from the past year. I'm an undergraduate researcher, and I joined in the middle of fall 2021. My first project was to work on the pick-and-place machine, and although it originally had a lot of National Instruments hardware, which was all very high-spec, high-torque stepper motors, and individual drivers for each, including power supplies, it's currently running off of an Arduino Uno, and I had to write a very lightweight G-code interpreter, as well as assemble a very customized stepper driver circuit. And right now I'm planning to upgrade that to an Arduino Mega and a RAMPS 1.4 control board that I pulled off of one of the disused 3D printers that we had. So that's what our current setup looks like. The wiring is of course very messy. It's very hard to decipher what's going on if you aren't already familiar with the components and the way that they need to be hooked up. And then this is the control board. It does look a lot more complicated as far as the items that are on it, but the wiring itself should be a lot simpler to decipher for anyone coming in. And the schematic for this is already published online, so it's not a big deal to walk into it. I also worked on the silicone printer. I helped address a lot of issues that we were having with it. One of the major ones was the extrusion mechanism. Essentially, the syringe pusher was reduced too much in its gearing. It was like 100 to 1, and it should have been about 10 to 1. So it was extruding far too slowly, and we had to design and implement a pass-through for that. Also proposed improvements to it in my earlier presentation, including a heated nozzle, continuous process, and using another printer as the basis of the next machine. Still looking at the best control system. It's going to take a lot of stepper motors to make that work. And before we spend any money on that, we're actually looking at how to effectively prove the validity of the continuous process, which is pumping the materials in, mixing them, and then extruding them. Pretty much all in the same step. Just hit go and have it all work out. So that needs to be validated before we move forward. And we already implemented and tested the heated nozzle, which you can see here. You can see the little bit of blue right here is actually from that attempt. It's not a big deal that it's there. It actually extruded just fine, which you can see here. These dudes noticed that there are some gaps and under extrusions. It was occasionally curing and clogging in the nozzle before pumping past it, and you can actually see, it's a little bit hard to tell, but there are some swirls going on. That's indicative of a partial clog causing some internal turbulence in the flow. Also helped set up the new IDEX printer, that's independent dual extrusion. I essentially was responsible for setting up the second extruder and the initial leveling, and I've leveled it since then. That's just general maintenance. Leveling is a bit of a misnomer. Really, it's tramming, so it's making sure all the axes in the bed are orthogonal to each other. And as well, I contributed to the tensile testing and multi-axis bender projects. I modeled the parts for these. Gianni printed them out and then did pretty much all the testing himself. I was able to help with the finger project as well. So we see the multi-material finger right there. That's a rendering that I did. We have some test samples that Gianni printed, and we have different core geometries. Here we have a video of the bender. Just kind of whipping it around, but essentially the idea is to have it be flexible in every direction, although this one does have some preference for twisting or tilting to the sides. So yeah. In the PowerPoint that's going to be located in the box folder, these are actually 3D models, so they can be turned around and oriented, so that way you can have a better idea. Unfortunately, they're not textured, otherwise I would have had the whole dog bone there. Yeah, that's it for me.
Great. I think it looks great, right? So let's give hands for Jacob Edwards. The combination of, Jacob, OV, and Gianni, they solved a lot of problems this year. And I think the result on the additive manufacturing area is significant. So I think that's great. All right. So the next, Jonathan. So let me display Jonathan and then we'll continue to the others. OK. Can you see the screen?
Yes.
Okay.
Hello, everyone. My name is Jonathan Lee, and today I present my research for HBS. So to get started, first, I fabricated some SMA muscles as shown right here. I have a whole presentation on how to create SMA muscle. So if you want to learn how to create SMA muscles, please use this link right here. I give you guys steps as well as a video demonstration of how to do it. But what I really want to focus on is the sealing of the Jellyfish Robot. I was mainly responsible for this part. So first, I had the idea to pretty much degas the epoxy mixture by using a vacuum chamber, because I thought I could treat epoxy as silicone and pretty much remove the air bubbles like that, right? But later on, I found that only certain epoxy would work with vacuum chamber, and the epoxy that we had would not work with the vacuum chamber. So I had to resort to the brush stroking right here to pop the air bubbles when you apply it onto the surface, as shown in the middle pictures right here. And on the right side is the final product of our sealing. But the main issue we had was like the water wasn't seeping into the 3D printed structure, but rather to the little gap in the O-ring right here. So we had to pretty much devise another way to seal it, right? First, though, we had to find the buoyancy level in here. So initially, we used rocks to kind of push down, weigh down the robot for it to be, so it can sink down, right? But we found out that was kind of inconsistent, so we used sand. We switched to sand for it to be more even and consistent, as shown here. So my goal was to pretty much find like the amount of sand that would allow the robot to be perfectly buoyant. But when I tried to do that, it was a lot of challenges, right? Because like the O-ring I shown on the bottom left right here, it wasn't very well kept together, right? Water kept seeping into it, so that completely messed up the measurements of everything. So then another thing was like this really like a bunch of layers that we use O-rings, kind of like it was really difficult to like rebuild together, right? Because I had to like take apart the cap and put back the O-ring together, and that was really tedious for like finding all the measurements, right? But after all figuring out all that stuff, we had the final product right here, as shown here. So we then switched to like a layer O-ring right here, which was infinitely much easier here, as shown here. There's a little one layer O-ring in here. Then we had the water test here, and when you test the water here, when you test the O-ring, as you see, there's only like very little water droplets that seep through, right? Which is amazing. Then here's the final test of it, of the buoyancy. We couldn't ever get to be perfectly buoyant, but as you can see, it's like very close, right? Very close. And then if you put on like a new stick to that, that'd be completely buoyant. And that's what I did for HBS. Thank you for watching.
Great. Thanks, Jonathan. So the ceiling problem has been solved, right, Pondip?
Right.
Mhm.
Right, sir. The ceiling
Yeah.
problem has been solved, and my goal is to complete the experiments for the battery powered jellyfish, the swimming experiments within the next week or so.
Yep. Yeah, the ceiling is one of the challenges in underwater, all this electronics and stuff. Mhm.
Yeah. Yeah. So what we found out was that whenever we 3D print with the ABS material, in order to make it fully sealed, it is always better to paint it with the coating.
Acetone,
The
acetone,
coating,
right?
yeah, yeah,
Mhm.
the
Or
acetone,
acetone, or the
yeah,
other one. What was the
epoxy,
other name? Okay,
uh,
epoxy.
yeah, the epoxy.
XTC. That. How about that?
Right, right,
XTC.
right, 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 right,
Mhm.
right. Yeah. So once we do that, the surface is completely sealed basically, and then in order to basically if we have got two parts joined and we don't want water to seep in through that hole, what we did was that we just casted silicon layers. So with the help of two layers, it basically acts as a very good O-ring,
Okay,
and that seals very well.
sounds good. Sounds good. Great. Okay, let's give hands to Jonathan, right, and Pondip also for mentoring. All right. So now I think I will unshare my screen so that you guys can present. Okay, who's next?
Okay, next is Egan. After that, Joshua. If we have, and then like we will move on. So next is
Okay.
Egan.
All right, let me just share my screen real quick. All right. Oh yeah. Apologies for the
Daddy,
background.
chill.
Hold on. Okay, sorry about that. I'm just handling
Yeah,
the background
no
noise.
problem. No problem.
With that aside, let us record the slideshow. All right.
Okay.
Is everything working? Can everyone see the slides?
Yeah, we can see the slide.
All right, and the laser pointer as well?
Yep.
All right. So, hello everyone. My name is Egan Wang. I am currently a junior in high school at Taylor High School in Houston, Texas, doing the UTD HBS lab meetings remotely, and I am here to recap what I've done for the 2021 to 2022 year. So, I'll keep this one pretty short and sweet, and I'll make sure it's not visually cluttered. So let's go. So my main focus this year has been on MEH, or multimodal energy harvesting. This has been a sort of group of technologies that focuses upon using multiple different approaches to energy harvesting at the same time, so that their synergy together can allow for multiple different benefits when it comes to energy harvesting. So this energy harvesting, as is pretty obvious, is mainly used for energy generation. And some of the benefits are that, number one, it's usually very size efficient, where the ability to combine multiple different energy harvesting approaches together will allow for more compact designs that can be used in things such as remote sensors that can be placed in places where conventional power designs can't be used. There won't always be a mains electricity out in the middle of nowhere where you want to have sensors for gathering data. So you can use energy harvesting in order to generate the energy when you need it, thus allowing for more sustainable designs that could be left alone for longer periods of time without needing to be without needing their batteries to be recharged, and without having as much maintenance required for their power. So with the areas of study that I've done, it hasn't just been in multimodal energy harvesting. I've I first started with a little bit of research on the fishing line muscles before moving into multimodal energy harvesting, which then moved on to frequency up conversion and a prototype design that I've made in conjunction with the HBS lab that focuses on trying to convert low frequency linear oscillation into electricity via frequency up conversion. Recently, I've also been doing some research into vortex induced vibration in order to collaborate with the potentially collaborate with the UT Dallas's HBS Lab's current project about underwater jellyfish robots. So far, what I've done is with oh there we go. So far, what I've done is number one, multiple extensive literature reviews about the current body of knowledge relating to multimodal energy harvesting. Number two, we've also attended late HBS lab meetings in order to be able to garner more knowledge about the subject and to participate in lab meetings with other group members in order to help give feedback on their others. And also within the context of multimodal energy harvesting, I've done number one, design ideas. Number two, prototyping preparations using things such as CAD models as shown to the left, as well as other preparations for prototyping, such as recognizing the different optimizations and materials that would be needed for our for this specific up conversion design that I've done. I've tried to keep it short and sweet, so that's basically all I have for the recap. Thank you.
Great. Thanks, Egan, for the presentation and update. So you've been doing excellent in the multimodal energy harvesting, I think. Well, that's great. Let's give hands for Egan, everyone. Questions? Do you have any question from anyone? All right, let's move to the next. We'll be going to the next. Yep.
Next is Joshua.
Yeah. Okay, Joshua joined us recently, right? So how long? Hi, Joshua.
Hi.
Hi.
Can you see my camera, or is it?
Not yet.
Yeah. So Joshua joined us recently, but he has already left as his bachelor's degree has been completed. So he won't be
Congratulations.
joining
So
us.
let's congratulate
Yeah, thank
Joshua.
you.
Let's give
Yeah.
hands everyone for Joshua.
Yeah. So
Well done.
he worked on the one of the jellyfish projects with me, the hydrogen jelly, and I think that he has its slides on them.
Okay, and now we
Yeah.
can see you, Joshua.
All right. Yeah. Can you see the slides?
Yep.
All right. So I joined the HBS lab in late March, and I was able to work under Pawanit to do some work on the hydrojelly. And so, as a bit of background, the hydrojelly was basically a jellyfish robot, which used SMA muscles in order to actuate the bell of the jellyfish. And so these muscles were powered by basically chemical reactions between hydrogen and oxygen, which would be activated by a platinum catalyst placed on the SMA wires. And so this work was actually being done to recreate a previous design worked on by Professor Tedeschi in, I believe, 2012. And it was done to recreate the design to do a bit more testing on it and to develop it further. And the design can be seen here, where we have the SMA wires, which will be used to actuate fishing lines inside of a silicone bell and propel the jellyfish. And so the semester goals and the work that was done were to, as I said before, make another robo jelly using the same actuation methods and to test different things such as sealing. And so when we made this new model, we did make some design modifications. And these included making the bell, or the silicone, which made of the bell, less thick. And we also made the steel springs, we had them bent at a lesser angle, which would allow for better propulsion. And after all this work was done, the Robo Jelly was assembled, and we performed a final sealing test on it. And afterwards, or future work, should include actually having the platinum catalyst inside on the SMA wires, so that actuation using the SMA wires can be tested. And so here is the final result of what I worked on over the semester. We can see a top and bottom view of the Robot Jelly, as well as the silicone sealing, which was done for the final test. And here we can see the end caps, which are attached to the SMA muscles, as well as this silicone bell with the spring steels embedded inside. And on this slide, we can see the pipes on the inlet and outlet of the Robot Jelly, which were used for the final sealing test, which was successful. And that is about it for my work.
Great. All right, let's give hands for Joshua. Good job, Joshua. So this work has been completed. Very nice and clean work. So on this prototype, very neat. Mm-hmm.
Yeah.
So you just graduated, right, Joshua?
Yeah, that's right.
So what's the next plan?
So as of now, I will be applying to master's programs at other colleges.
Okay. Yeah, you've been excellent also to the smart material class, so that's great.
Yeah.
Yep. And thanks
thank you very
for
much.
contribution. Okay. Any comments, question for Joshua? All right. Okay, let's move to the next.
Okay, next we have Ishan, I think.
Yeah,
Ishan Navendra. If you can share your slides.
Oh, you're presenting, right, too? The next? Is that
Ishan?
next?
Yes, I'm present.
Okay. It says EOS. Here we go.
Let me.
Just before Ishan starts, we will be meeting on this paper with you, Professor, next week or sometime.
Sure.
So for this past year, I worked on a couple projects. First, I worked on the IRB application for the iGrab Duo project, and then that was in the fall. And then this spring, I mostly worked on a TCP muscle comparison project. And so my job was to help Drew set up like the IRB application, or help create like the like the human subject trial procedure. So I looked through some upper extremity tests that could be used to test the iGrab and decided to go with the action research arm test. Due to its fairly simple concepts, and the scoring system is fairly detailed, so it is easier to discern the differences between the iGrab and or a hand using the iGrab and one that is not using the iGrab. But then this past spring, I switched projects to work on the TCP muscle comparison project, which the goal is to compare 2-play, 4-play, and 6-play TCP muscles. And we also planned on discussing applications and creating PID controller to maximize muscle efficiency in terms of temperature. But the last two parts may or may not be included in the paper. So for the first half of the semester, I mostly was focused on fabricating and training muscles. And as the chart you can see here shows pretty much all of the muscles that were fabricated for this project. And once we finished fabricating and training the muscles, we switched to characterizing them. So we loaded a 2-ply, a 4-ply, and a 6-ply muscle onto the characterization setup, and we ran many different trials, and each trial measured the voltage across the sorry, it measured the voltage across the muscle, the current through the muscle, how much the muscle was displaced per cycle, the force the muscle exerted, and the temperature of the muscle. And the table on the right shows like how trials were broken down. So for 2-ply muscles, we varied the weights, currents, and time current was applied to each muscle. And we just did that for a total of 135 trials. And so we just completed that this past week, and we're hoping to finish writing the paper in the next few weeks for publication. And that's all I had. So
very nice. I like this slide. So I think the combination, the one that you have in this, yeah, 2-ply, 4-ply, the current, the load, and the heating and cooling time. So I think that's good. All right, let's give hands for Isha Navendra. Questions from anyone? Okay, so let's go to the next.
Okay, next is Arwa.
Arwa is new, so she's not presenting, right? So she's just joined. Always, I think. Always is the one.
Yeah, is the last one. Always.
Can you guys hear me?
Yep.
Share my screen. Can you guys see the presentation?
Yep.
Hi, my name is Oves, and I recently joined the HBS lab. So right now I'm in the process of reviewing the different kinds of hands, artificial hands that are developed at the HBS lab. Today I'll be presenting the SMA Actuated Hand that was developed recently at the HBS lab a few years ago. So the design objectives for this hand were that it should have the ability to hold at least 100 grams, and it should cost less than $200 to fabricate. And then the arm and structure should be less than 300 grams in weight total, because it becomes uncomfortable because you have to wear the hand if you're suffering from a stroke or whatever other purpose you're using it for. And it should also have the ability to manipulate objects of daily use, about 50 to 100 millimeters in size. And then it should be easier to manufacture so that others can modify and print it according to their needs. And then the size should be the size of a typical adult hand. And then it should operate silently. And then room temperature should be optimal for its operation. So some other preliminary considerations were that most artificial hands were extremely expensive. So the prices range from $6,600 to 100,000. And then most of the hands that exist are highly complex because the standard hand uses electric motors. And for this, they use joints to incorporate every degree of freedom into the design. And because of this, they're highly uncomfortable to wear because of their complexity and their weight. And some new promising actuators for hands are SMA, shape memory alloy, and twisted coil polymer, or TCP. This is because they're low weight and then they have a simple working mechanism. You basically heat them and then they contract. So the major benefits of using SMA muscles are that they're compact in size, they have a high force to weight ratio, and they operate silently. Some downsides are that they have a low energy efficiency and a low stroke and low operational frequency. The frequency can be treated by using an external cooling source because when SMAs are heated up, they take time to cool. If you use an external source, it can increase the efficiency of the operation. In terms of the stroke, it can be improved by using a helical structure. So if you use a linear SMA, then the 5% stretch stroke of it is lower than if you use a helical structure, because a helical structure will have a higher linear strength when it's higher linear length when it's stretched out. So in this hand, we used a helical coiled SMA to generate higher stroke. And then comparing it to TCP have high strokes, but then we solve that using a helical structure. And then they're inexpensive and they have a high force output. However, they have a low frequency and they also require high inputs. But another downside to them is that they have an extremely limited life cycle. An example of this is that they have a predicted life cycle of 800 cycles at 0.25 hertz in water. And this is the Creo model of the hand. It uses ABS structure for its base, and then it uses tendons, and then the coiled SMAs are above the perforated deck plate. And then the working mechanism of the hand is shown in the picture below, which shows that there are two SMAs for every finger. One is to flex the finger, and the other is to get it back to its unactuated state. So it generates opposite motion. So the upper one, when you actuate the flexor muscle, it contracts and the finger bends. And then when you actuate the extensor muscle, it generates opposite motion and makes the hand return to its unactuated state. The thumb motion is only flexion and extension right now. The other motions aren't incorporated into this design because of their complexity. So this is a comparison of this design, this coiled SMA, which is the last one in the table, to other coiled SMAs, SMA plates, and then SMA wires. So we can see that this one has the lowest weight and this one has the highest degree of freedom to actuator ratio. So it uses 8 actuators and we get 14 degrees of freedom. It also has a lot of fingers, and then which the others don't. So for the fabrication, 2 stepper motors, a mandrel, and then a linear motor, and the SMA wire was used. So the winding motor draws wire from the pool, and then an unwinding motor coils it around the mandrel. And then the linear screw motor controls the pitch, which moves downwards. And all this happens as the coils are being wound by the winding motor. In terms of the circuitry and actuation, 8 metal oxide silicon field effect transistors were used, and a regulator that was soldered to a breadboard was used, and then a microcontroller, Python PyBoard microcontroller was used. So each transistor receives pulse width modulation signals from the microcontroller, and then the transistors functionally reduce the battery voltage while the pulse width modulation to the necessary power, and then it provides it to the muscle for actuation. And then the power is provided from a rechargeable battery that is shown in the schematic diagram. Experimental setup for the experiments that were used, we used laser sensors, thermocouples, and then the SMA was set up, and then a linear guide with a bias spring was set up. And then the SMA was loaded into a load cell and then connected to the linear guide. And then the tests that were conducted were finger bending angle tests, horizontal grasping tests, vertical grasping tests, frequency tests, and cyclic tests. So this is the muscle characterization tests or the bending tests. So in this, the maximum temperature in the results for this, the maximum temperature was not reached until the second or third cycle. And the peak temperature was 99 degrees Celsius. But the large variations in temperature didn't create a significant change in force or displacement, since we see consistent force and displacement changes in the diagrams below. So this is one of the aberrations that we observed. And then as for the electric current and angle tests, we used 0.5 amperes and then 0.3 amperes. We also tried using 0.2 amperes, but the input didn't create noticeable actuation. So the angular outputs from the MCP, PIP, and DIP joints were consistent for 0.3 and 0.5 ampere currents. However, there was a slight aberration in the returning phases of the 0.5 ampere actuation. And then on the bottom, there's an example of the physical hand being captured in different phases of the actuation cycle. So the horizontal grasping tests was conducted using a cricket ball, plastic cup, and then a box. So the heating cycle that was used was 0.5 amperes were inputted to the flexor muscle for 4 seconds, and then 0.2 amperes were pulsed to the flexor muscle to maintain the grip on the object. And then a 1 second off period was left. And then for 7 seconds, 0.5 amperes were applied to the extensor muscle to make the fingers return back to their original state. So this process was relatively non-cyclical because it included only one grasp and release. So we didn't see the aberrations that we saw in the cyclical current input test that we showed previously. And then this was relatively smooth, and this resembled a human hand grasping an object horizontally. As for the vertical grasping tests, an empty cup and then a cup with water and a box that weighed 12.67 grams, and then the same box was used. Same box as last time. So the thumb in this is not used, so the gripping is solely generated from the fingers. The thumb provides no support. And then first we make the hand hold the cup, and then we pour water into it. And we can see when we pour water into it, the cup sinks into the hand because of the increased weight. And then the current supplied for the vertical grasp test was the same as the horizontal grasp test. Only the duration of the current was increased by 2 seconds for all of the flexor muscles. And then 2 other tests were performed, the perpendicular loading tests. So the perpendicular loading test was accompanied by a perpendicular loading simulation. So a large displacement is seen in the simulation, but this is because we used a cantilever approach. We applied a load at one point, and this isn't generally the case in hands. So, however, even despite the cantilever arrangement, the displacement wasn't as large as we expected. So this shows that the finger can sustain high loads without yielding. And then a regular gravity test was also performed experimentally and using simulations. So in the regular test, we see that the angle isn't as much as the simulation. This is because in the actual hand, we're using antagonistic muscles. So we can balance off any high aberration in terms of displacement. We can balance it off by generating motion in the opposite direction because we're using coupled antagonistic muscles. And then in terms of the frequency test, 3 tests were performed. 8, 10, and 12-second cycles were used. And then the current heating method was the same as the horizontal grasping test, which is 0.5 amperes for 2 seconds, and then a 1 second off period, and then a 0.5 ampere for 4 seconds for the first test, 5 for the second, and then 6 for the third to the extensor muscles. So the maximum frequency that was achieved was 0.125 hertz. This is very low compared to the 2 hertz frequency of an actual human hand, but the frequency can be increased using an external cooling method, as mentioned before. And this is also demonstrated by another paper where they used circulated water to increase the efficiency, and then the frequency they got from the external cooling using water was 1.7 hertz.
Mhm.
And as for the conclusion, the results demonstrate that the SMA actuated TPU hand is capable of carrying significant amounts of weight, and then they have a relatively fast response and flexion time. And as shown before in the table, we see that this hand is lower in weight, and then it generates no noise. And then the power density is high because we use low amounts of actuators and we get higher amounts of degrees of freedom. And the muscle outputting force is about 300 times the weight of the actuator used. And that's all I have for today.
Great. Thanks, always. I think this is a good refresher for the hand that the TPU hand, right? Okay, let's give hands for Ois Najam. Good job. It's a little more time, but I think it's good refresher because that work is good to look at from that point. Mhm. Okay, I think we are done, right?
Yes.
Yeah, so
We are done.
I think it was a very good discussion and meeting summary from everyone. Thank you so much all for contributing this. I think we should continue this kind of activity. I just want to say that despite difficulty we had last year, I think we have significant results. Personally, myself has a very difficult time this year because, as you know, my dad passed away. It was very hard for me. He was a friend. He was also a mentor. He's a father, everything. So research-wise, somehow our research is affected because I was away. And but I think you guys did very well, and I'm so happy that we have achieved significant result. Thank you so much, all of you. Thank you for contributing to HBS Lab and also for your personal career. Okay. The next thing is to wind up and summarize all these things in a publication. And I will meet you individually. Let's continue collaboration and continue the great work. Okay. Thanks, everyone, and enjoy.
Thank you.
Mhm.
Thank
I'm
you,
gonna
Professor.
thank you so much, everyone. So I'm gonna stay for some